Welcome back, everyone. In this video we're going to do problem number 4 of the chaotic review. And it looks like our goal is to go out and find a good C value, right? What value of C to make this function continuous. So this is a nice piecewise defined function. So if x is not equal to 1, it's going to behave like this rational function, right? F divided by g. If x is equal to 1, it's going to behave just like the constant C. And we want it to be continuous. All right, so continuity, this was an idea that we brought up back in 1.8, right? The section's name was continuity. And in the definition of continuity, the whole deal with it is like as you approach a value, so as you approach, let's just stick with a for right now, for our function maybe h of x, right? If this limit exists and all that stuff, we want it to be equal to h of a. So the limit, what you approach, is actually equal to the function's value. And this is what it takes for h to be continuous at a. So we want it to be continuous at 1, however, so we would like to switch these out, and as you approach 1, right, this should equal h of 1. So again, maybe let's actually graph this out really quick and kind of show you why this definition works, because it's been a while, right? So I'm going to go ahead and draw a quick mini graph here at 1. And suppose, I don't know what h looks like, I'm just going to kind of go crazy here. So let's suppose h looks something like this, right? So here's my h function. So suppose, right, the limit exists and all that good stuff as you approach 1. And right now there's a hole, right? Remember, this was called maybe a removable discontinuity, right? So there's this hole right here. And we were like, well, first of all, maybe if h of 1, right, the height of the function at 1 is something up here, well, then that's not going to be continuous, right? Again, it has this removable discontinuity. However, if as you approach 1, again from the left and the right, this is the two-sided limit right here, if that is equal to h of 1, if that limit is equal to h of 1, then you've effectively filled in that hole, and it is continuous. Okay, so again, our goal is to go out and find this good C value, right, which makes h continuous. So let's go ahead and take a look here. So h of 1, right? So h of 1, so I'm here in my h function. H behaves two different ways. If x is not equal to 1 versus if x is equal to 1. So I want to plug in 1 here. Well, that means I'm in the second category. So h of 1 is equal to c. So h of 1 is equal to c. Now, let's try to evaluate it. What is this limit, right? So we know the limit as x approaches 1. Remember, the limit means it's really, really close to 1, but it's not equal to 1, right? So in this case, really, really close to 1, but not equal to 1, I'm actually going to be in this first category, right? Because I'm not equal to 1. Really, really close to 1, but not equal to 1. So this is going to be the limit as x approaches 1, not equal to 1, of h of x. Now again, h of x, it behaves like f of x over g of x, so long as we're not equal to 1. Okay, so f of x divided by g of x. So here's my f of x function, x squared plus 2x minus 3, divided by my g of x function, x squared minus 1. So again, that was a decent amount of interpretation, but now we see that we would like C to be equal to whatever this limit is. So if we can evaluate out this limit, whatever that answer is, that's what we want C to be equal to in order for h to be continuous at 1. And so now we need to think back on how do I evaluate limits, right? So usually the first thing that I do in an evaluation for a limit is I see what happens if I just plug in 1 everywhere I see an x, right? So if I go ahead and plug in 1 everywhere I see an x, let's see, in the numerator I'd have 1 plus 2 minus 3, and then in the denominator I'd have 1 minus 1. So this would be, let's see, 3 minus 3 would be 0, over 1 minus 1 would also be 0. So I'm in this 0 over 0 situation. So this tells me how I need to start thinking about this problem, right? When you're in a 0 over 0 situation, you're looking for those zeros to cancel in some clever way, right? And usually there were like 3 or 4 techniques that we had in order to try to cancel those zeros. Remember, we had stuff like getting a common denominator, or factoring, or multiplying by a conjugate. And we know a little bit about the sine of x over x business, right? So in this case, because I have a nice polynomial over a polynomial, I'm going to try factoring. right? Because there are no square roots, so really multiplying by a conjugate doesn't really make sense here. We already have a common denominator, so that's not really going to help us. There's no trig functions like sine or like tangent or anything like this, so really my main hope is by factoring. So I'm going to try to factor the numerator and the denominator and see, hopefully this turns out with something good. So x squared minus 1, that's a difference of squares. I know that's going to be x minus 1 times x plus 1. And of course I can FOIL that all out and see that I get back to where I started. So this is indeed equivalent to x squared minus 1. Now how about in the numerator? Right? I think this also factors. Let's go ahead and try here. I'm going to try x plus 3 and x minus 1. Let's double check. If I FOIL this all out, I'd have x squared. Let's see, I'd have plus 3x and minus x. That makes 2x, good. And then 3 times negative 1 would be negative 3. Excellent. So this seems to be working out. And again, we want whatever that limit is to be our c value. And I can see now that by factoring, actually we have an x minus 1 on top and an x minus 1 on bottom. And that's our main culprit, right? By plugging in 1 everywhere we see an x, it's making that term 0 and that term 0. All right, but now that we've canceled this, we're going to have the limit as x goes to 1 of x plus 3 over x plus 1. And that's going to be, well, now there's no problem with plugging in 1 everywhere I see an x. So I'm going to have 1 plus 3 is going to be 4, divided by 1 plus 1 is going to be 2, so that's a total of 2 altogether. And again, that's my limit, so that's what I want the c value to be. Because again, if I let c be equal to 2, that limit there, then we've effectively filled in that hole, right? We want c, the value of h at 1, to be equal to the limit, right? What happens as we approach 1 from the left or from the right. All right, so our answer here is C. But man, there's a lot of interpretation to this problem before we actually see that this is a limit problem. And whatever that limit is, that's our answer. But again, it takes a little while to get there. All right, that's it for problem number 4. I'll see you guys next time.